Okay, let's not talk about that anymore. Let's carry on. Okay, so last time we introduced the notion of the Higgs mechanism as a sort of functional means of starting with a theory that has a gauge symmetry and therefore has massless gauge particles, and then you can kind of functionally give the gauge particles mass. Today we're going to flesh that out. A lot of you have computers open. Why? What are you doing?
Your book.
Avery, what are you looking at?
I am looking at volume 1 of your textbook.
What are you looking at?
Volume 1.
Wow, you guys are insane. Okay, all right, that's the right answers. Good job, guys. Okay, so what we're going to talk about today is a very important part of the Higgs mechanism, which we didn't talk about so much last time, but it's going to play a critical role today, and that is the notion of broken symmetry. And of course, you should remember that the Higgs mechanism is sort of an important part of the breaking of SU2 left cross U1 hypercharge into electromagnetism. So today we're going to flesh that out. So first and foremost, let me just go through a sort of dumbed down version of broken symmetry, and then we'll get into a more sophisticated version as it applies to the Higgs mechanism. So it is possible, and I think my black marker is going to give out, for a solution to the equations of motion to not exhibit the symmetry of the original action. So let me give you a simple example of this. Man, this thing is just, it's going. It's going to be gone soon. Golly, I don't know what the hell is wrong. Let me do this in blue. Maybe blue will work. Do you see any black markers in the rest of the room?
I have one in my backpack. You want it?
Let me see if I can get away with blue, but I will keep you on deck just in case blue gives out. So, it's not looking great, but it'll be okay. So, all right, so let's pretend we've got a scalar field, and our scalar field is enjoying a potential which has the following form. So I have a quartic term with a negative sign in front, and we have a quadratic term with a negative sign in front, a quartic term with a positive sign. And then if we plot this, just a rough sketch of it, looks something like that. And our Lagrangian is just going to be the spin zero Lagrangian minus the potential, okay? And I'm actually going to give you the equations of motion this time, just to refresh your memory on how equations of motion for fields look, because we're going to use these in the near future. Okay? So if we have a scalar Lagrangian, or if we have a Lagrangian for fields and we want to find the equations of motion, we just take the derivative of the Lagrangian with respect to the field times the derivative with respect to all coordinates, so this is t, x, y, z, of the derivative of the Lagrangian with respect to the derivative of the field. And in this case, this is just going to give us that as our equation of motion, okay? So as I promised last time, static solutions, which are commonly the solutions that we will use for background fields. They're just a constant value of the field everywhere. So we just want to take d mu of phi equals to 0. That eliminates this term, and therefore we just want dv d phi equals 0. Okay? And this, of course, is minus phi plus phi cubed equals 0. Okay? Now, I didn't actually need to do that. I could have asked you, what are the 3 static solutions with this being the potential, and you could have pointed to them, right? Where are they? Yeah, there's one here, there's one there, and there's one there. How do you know that? I mean, if you start here and you have no initial motion per se, you'll sit there happily. If you start here and you have no initial motion, you'll sit there happily, and if you start here, you'll just sit there, okay? If you start anywhere else, the evolution of the field is definitely not 0, okay? So this is hopefully just a reminder of, Ekström as being reflections of the vanishing first derivative. But here's where it's interesting. Okay, so for the solutions to this, we have 3. We have phi equals 0, we have phi equals +1, and phi equals -1. All right? Now, I want to ask you a question, and I'm going to ask this question of Madison.
You didn't even look. Okay, it is.
The Hierophant. The Hierophant. Madison the Hierophant. Is this potential symmetric under sending phi to -phi everywhere?
Yes.
Yes. Give her a hand. Hunter Leon. You ready?
Yeah.
Is this solution to the equations of motion symmetric under the exchange of phi goes to -phi?
Yes.
Yes. Hold on, because he's got to answer 2 more. What about this solution?
No.
No. And the last one?
No.
No. Give him a hand. Okay. So I'm just pointing out that even though the potential which governs the dynamics has a symmetry, okay, solutions don't have to share that symmetry. Okay? And this is a basic point, but it's going to get enhanced when we actually look at the potential associated with the Higgs. Now it gets even better because we can consider the fluctuations around a solution. Okay? Because remember, in doing particle physics, what our operation is we solve the classical equations of motion to get a solution. And again, we don't have to start with a static solution, but these are the most commonly used ones. So we get a static solution. There's 3 here. But then, if we're interested in particle behavior, what we want to do is we want to let the field fluctuate about the solution by a small amount, and these are going to represent particles. Okay? So of course what we can do is we can take this and we can shove it into the Lagrangian, and we get, if we do that, we get the following, and the work associated with deriving this is in my notes, but I'm not going to write it all down. We end up with the following. Okay? And I, for some strange reason in my notes, decided to drop off the 1/2 and the 1/4 factors, but they're not really that important. Don't worry about it. Okay, so now I want you to notice, if we take phi naught equals 0, if we take the 0 symmetric solution and we consider perturbations about this solution, then L delta phi just becomes the kinetic term minus, well, there it is, delta phi squared plus delta phi to the fourth. Okay? Is this, let me pick another name, Joshua Moller. Glad to see you voted. Or, as Madison accused me, you stole a sticker. It's fine, we don't need to discuss it. I voted, but stole a sticker. So figure that out. Anyway, is this symmetric under delta phi goes to negative delta phi?
Yes.
Yeah, I mean, this is quadratic in delta,
Yeah.
sorry, there should be a delta there. This is quadratic in delta phi, so if I swap delta phi with negative delta phi, the same remains the same, and this is quadratic in quartic, so the minuses just disappear, okay? However, let's take plus 1 as our solution. And I've still got you on the rope, that's why nobody has clapped. But they will. Is this solution invariant under if delta phi goes to negative delta phi?
No.
No, okay. So again, I'm just reiterating this point that you can have an invariant action, which is of course the integral of the Lagrangian with respect to d4x, and we're really just focusing on the potential because this is the only thing that is a function of phi. This has this symmetry under phi goes to minus phi, but a solution and the subsequent fluctuations about that solution cannot have that symmetry. They can have it, but sometimes they can't. Okay? Or sometimes they don't, is what I should say.
Will people clap for me now?
Huh? Oh, yeah. Okay, all right, so let me just write up here. Whoops. Okay, so there's the mathematical notation of we have the symmetry, we don't have the symmetry. Okay, now, I'm going to apply this story to the Higgs mechanism. Okay, but I want to do a very quick rundown of the results of the Higgs mechanism from last time. So, and I won't write down, I won't write down everything I wrote down last time, so Avery, stay in your seat. No need for you to come and tell jokes.
But it's her birthday.
It is his birthday.
Yeah. Let's tell those jokes.
Okay, all right, yes, all right.
Oh.
So remember the Lagrangian for the Higgs story after we gauged the U1 symmetry that was present. So maybe I should call Avery up to tell some jokes, but I'm not going to give in. Avery, sit down. Sit down, Avery. You're up.
Hear the rustling.
I know, it's pretty terrifying,
So
in all honesty. Okay, anyway. Good God, this is long. Okay.
Yeah, really. I got a bunch of good ones.
I believe you. I totally believe you. All right. Okay. Now, now notice the potential. Phi star phi and phi star phi squared. Okay. This takes on a lot of what I just talked about, except we're going to discover that this is slightly more complicated. But in review what we did last time, we have a symmetric solution which corresponds to phi equals 0 and a mu equals 0. And this basically gives us a Lagrangian for the fluctuations about this solution, which has the exact same form as the Lagrangian we started with. You really just take this and everywhere you see A, replace it with delta A. Everywhere you see phi, replace it with delta phi. Everywhere you see phi star, replace it with delta phi star. Okay? And just remember, phi is a complex field. It's got a real part phi 1 and an imaginary part phi 2. If you're saying phi is 0, then both of those are 0. Okay? And then we considered the non-symmetric solution, where in particular we took phi 1 as mu over lambda, phi 2 is 0, and a mu is 0. And we redefined our fluctuations. Delta phi 1 is eta, delta phi 2 is beta, and delta a mu we just called a mu. And then this led us to a Lagrangian of the following form. And I'm not going to write the entire Lagrangian, I'm just going to write down the kinetic terms. And I'll leave out all the interactions. Okay? There are a lot of damn interactions. That's why Avery got up and told jokes. We don't need Avery this time. This is pretty short. We don't need Avery this time. This was short. Anyway. Okay. Now, notice this kinetic term represents massive field fluctuations for eta. Okay. This field is, of course, massless. There's no mass term for it. And then, of course, and this is the magic of the whole mechanism, this corresponds to a massive field, a mu. Even though, in the theory that we started with, the gauge field had no mass term. But by choosing this solution, we've suddenly generated a mass term for that gauge field. Okay? Now, what I would argue is that choosing this solution versus choosing this solution is much like the solutions that I considered for this, where that corresponds to that solution, and this corresponds to that solution. Okay? But we really need to see what this looks like. So now you're going to see the picture that underlies the Higgs mechanism. Put your hat on. It's time to go. So, what in the world does the potential for that look like? Yes, that's exactly right. No, it is the
Sombrero.
It's the Mexican hat potential. Yeah.
Isn't it kind of like an upside down bundt cake?
No. A bundt cake pan is a sombrero shape. The bundt cake itself is solid.
Yeah.
You guys really.
Guys.
I'm sorry.
Anyway,
Yeah.
here we go. So the Higgs potential. Okay, first of all, I mean, this looks a lot like the potential that I did earlier. Okay? And in fact, if you just relegate yourself to real fields phi, this is the potential I gave earlier. It's that, you know. So all you're doing is, through making phi complex, you're taking that potential and you're revolving it around the axis of the potential. So here we go. Here's our picture. That's the only circle I'm going to draw, but you could draw lots of circles to encourage that this thing is actually a hat shape. All right? Okay. Now, again, I am using U1 for the gauge symmetry of this, and this is actually a plot of a U1 symmetric potential. This is not the actual realization of the Higgs mechanism in the standard model. The real mechanism in the standard model is breaking SU2 left cross U1 hypercharge, which is a considerably more complicated picture. But this is nice for illustration purposes, and it contains all the same ideas, so I'll just take you down this road. Okay. So let's start by identifying the solutions. So there is your phi equals 0 solution. Okay? And now we immediately notice something interesting. How many other solutions are there? How many?
Infinite.
Yeah, where are they?
All around that bottom circle.
Yeah, any point on this circle, which is the minimum of the potential, corresponds to a solution, okay? And so we can classify these by any solution for which phi squared is mu squared over lambda squared, okay? Solutions. It's a set, it's not one. Okay? Now, I want you to forget this for a moment. In fact, fuck this whole thing, just ignore it. Okay, if I could lower the screen, can I lower the screen? And that's the.
This is way too challenging.
It's on the podium.
Yeah, I'm not going to do it anyway. Just ignore this. Just ignore this for a moment. Okay? Sorry, Charlies. Okay. Where in our ring of solutions is this solution? Let me ask. Well, okay, I got to load up my next person, but I won't ask them this question because I have plenty of volunteers. All right, but I've already gotten the answer to this one. It's where? It's where? The whole ring of solutions is at the tip. Yeah.
It's on the positive real axis where the circle intersects the positive.
Yes, it's right there. It's when the real part is non-zero and the imaginary part is 0, so this is the solution right there, okay? Now, I want you to think about the fluctuation delta phi 1. That's the fluctuation along the real component. So you're talking about a fluctuation which, if it fluctuates, it has to climb up this thing, okay? So that's your eta fluctuation. What about your beta fluctuation? It comes, along the circle basically. So out of the board or into the board. Does it have to climb up any potential?
No.
No, okay. Now I can sit and I can look at that picture and I can immediately tell you eta has mass and beta doesn't. Now I know you can get it from here. But how can you get it from here? Nico.
Because it requires energy on the eta place, which implies that. Never mind.
No, keep going, keep going. Yeah, I mean, to fluctuate in eta, for the fluctuation in eta to exist, requires energy to exist. You're moving up the potential. Whereas a fluctuation in beta, it's not costing you any energy. So you can say, like, for an eta fluctuation to exist, you got to have energy. That's like mass. You know, for you to exist, if you have mass, it requires energy. If you're massless, then you don't require that energy. Okay? Well, let me give you the more methodical way that we approach this. The methodical way that we approach this is if we take a potential, then what we do is we can expand that potential D there, I don't know why, but I'll just write it down. Okay? And now this is a potential, okay? But notice the quadratic term in a potential is playing the role of a mass because it's basically a quadratic in the field times some constant. But that's exactly what a mass term looks like. Okay? So if you just have the potential and you don't know anything about the mass, and you look at the concavity of the potential at different points, that immediately tells you about the mass. Okay. Concave up, the fluctuation is a mass. If it's flat, it has no mass. What about if it's concave down?
Negative mass.
It has negative mass. So this is what would give rise to tachyonic fluctuations, which we talked about before. Okay? Go ahead.
What if we're at the point where phi 2 equals mu over lambda, and then phi 1 equals 0? So
Where phi 2 equals mu over?
yeah,
So
right
here?
Yeah. What's that? Because it's a sombrero, so wouldn't that mean that now fluctuations in beta have a mass? Or is
Well, so here fluctuations in phi 2 would have a mass, fluctuations in phi 1 would not have a mass. So yeah, if you're going to call fluctuations in phi 1 eta and fluctuations in phi 2 beta, then beta would have a mass and eta would not. Yeah, I totally agree. Okay. Now, so now let me ask you a question. So our original symmetry that we gauged was this symmetry. Phi goes to e to the I theta x of phi. Now this is a gauge symmetry. And one of the important things that you will eventually, hopefully, get to learn about gauge symmetry, which is not going to be obvious towards the end of this class, but it is the truth, is that a gauge symmetry is fundamentally different from a physical symmetry. Okay? A physical symmetry is a symmetry such that if we do a transformation on a system, we actually change the external states or the asymptotic states. So for example, rotation is a physical symmetry. If I take an experiment and I rotate it, and I'm considering the experiment where the particles shoot out like this, then the particles now shoot out like this. That's a different result than this. Even though if you have a rotationally invariant system, you would expect to calculate the same amplitude. That's why the rotation is a symmetry. You get the same physical observables, it's just they're going out this way instead of this way. Gauge symmetry is sort of different. Gauge symmetry, if you do a gauge transformation, it never touches the things that are coming out that we physically observe. All that a gauge transformation does is it lets us rewrite our description of what's going on. So in fact, a gauge symmetry is really a redundancy in the way that you're describing something. Okay? There's more than one way that you can describe the same thing. And transferring from one description to another is a gauge transformation. Okay? So this is the gauge symmetry. What transformation in this picture does that gauge symmetry now correspond to if we pick this as our solution? It's exactly, it shifts in beta. So let's think about this for a moment. I said that the resulting theory in terms of these fluctuations comes out like this. We get a massive field eta, massless field beta, and a massive field for the gauge field a mu. However, I just made the argument that a change in beta, and this includes fluctuations, I mean a shift in beta can be a fluctuation in beta. I just made the argument that a fluctuation in beta is non-physical. Whereas the fluctuations in eta and A are physical. So there's a certain sense in which this beta doesn't really exist as an independent particle-like fluctuation. Now, let me name these for you. The fluctuation in eta, the one that has mass, remember it that way, the fluctuation that has mass, that's called the Higgs boson. That is a particle in the Standard Model, which of course we experimentally discovered back in like 2012, I think. Beta gets a temporary name. It's called a Goldstone boson.
What do you mean by temporary name?
Because we don't really want beta to be in the theory. Beta is not like an independent particle. But it turns out there's an important role that that beta plays. And this is, Joel, I'm so glad you're getting this question. Because it's going to suck. All right. But I want you to think deeply about it. We started with this Lagrangian, with a massless gauge field. And by picking this, now we understand symmetry breaking solution, we, among many things, introduced a mass term for the gauge field. You ready? What other question about that gauge field could you ask to which there better be an answer?
Can you give me a hint?
Yes. If I want to take a massless particle, and in particular a vector particle, and I want to transition it into a massive particle, what does that change about that vector particle?
I don't know what you're looking for.
It changes the number of polarization states.
It changes the number of polarization states. So you'll have to go back to the, oh man, what's his name? Somebody help me with his name. The guy who did the classification.
Avery.
Say it again? No, not Avery. No, anyway, it's my memory. So, yeah, huh? Yeah, Wigner, thank you. Yeah, Wigner. So remember, if you have a particle which is moving with some momentum, which is not moving at the speed of light, then you can go to the rest frame of the particle, where there's no momentum, and then you have SO3 as the set of rotations which don't change the momentum. Boosts change the momentum, so you want transformations which don't change the momentum. So if it's massive, you go to the rest frame, you have 3 independent rotations, and this of course gives you 3 polarizations. However, if the particle is massless, you cannot go to the rest frame. The simplest frame to go to is that one where you have all of the momentum along one axis, say the x-axis, okay? But at any rate, the only transformations you can do that preserve this are SO2 rotations, and that yields 2 polarizations. But the important thing is that each polarization of A mu is sort of a degree of freedom of the field. And the important moral to this story is that A, because it has no mass, has 2 polarizations. This A, because it now has mass, should have 3. Where did the third one come from?
So did the information, because we have 2 sets of independent bits of information up there, when we created this thing, is that why beta is not like a real thing?
Exactly.
Okay.
In words, A eats beta. This is the way that this is the terminology that we use in high energy physics. Okay? The gauge field in gaining mass is eating the Goldstone boson. So what we can do is we can leave the Lagrangian like this and say A mu only has 2 polarization states, which is weird. Or we can just erase this and say A has 3 polarization states, which is way more normal. Okay? And notice, this is a scalar field. It has 1 polarization. It's the size of the thing. So it is exactly what the A could use in fleshing out 3 polarization states instead of 2. Okay.
Dr. Klein,
Yeah.
What do we mean by a polarization state?
What do we mean by a polarization state? One way to count it is to just count the number of angular momentum states associated with the spin of the particle in normal quantum mechanics. Don't think about it in relativistic quantum mechanics, because when you do the Wigner classification, often you're reducing it to SO3, which is the 3-dimensional rotation group in non-relativistic quantum mechanics. So just count the number of angular momentum states. So spin 0 has 1, spin 1/2 has 2, spin 1 has 3. Okay. All right. So okay. So when the theory, okay, so now I should say, let me make sure I'm going to say this. The overall symmetry of this potential is preserved by which solution? Yeah, it's preserved by the 0 solution explicitly. Okay? Well, let me ask you a question. If I come down here, do I still have symmetry, the symmetry of this potential? I mean, is the symmetry really still there? Yeah, because you can move around the ring and things don't change. So the symmetry of this shaped potential is really there even in these seemingly non-symmetric solutions, but their presence is by the satisfaction of the Lagrangian under that gauge transformation. Okay? So now, in the history of the universe, okay, so I should just go ahead and add this picture, which is it's a 3-dimensional picture with a 2-dimensional surface potential that's drawn in there. This is all you need for U1. Okay. Would anyone like to come up to the board and try and draw the potential associated with that gauge symmetry group? You want to do it? Come on.
Yep. I can do this. I can do this. I even have my own marker.
Okay, go for it.
Okay. So I know in higher dimensional things, you just like sort of draw an amorphous blob, and then that's it's perfect.
Awesome. Right, give him a hand. Yeah, and that's pretty much right. All right. So anyway, clearly, look. Clearly, there is the picture that gives you an intuition. I mean, you know, it's nice because you can say, oh, this is concave up, therefore that fluctuation is massive, blah, 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 blah. But if you want to work with this, there's no picture, no two-dimensional, three-dimensional picture. So you really need techniques like this, like expand the potential, look for the quadratics in terms, and those are going to be associated with the masses, et cetera, et cetera. So for example, if you do U5 for the beta, then the quadratic term will vanish identically, okay? So I'm just saying, like, you have to go back into the functional formalism to extract these things in the SU2 left cross U1Y. But this picture is a useful, intuitive reference. Now, one more thing is that in all of this story, I have only shown you how to give a mu mass. But you might remember that there's a few more things in the standard model Lagrangian, like all of the matter in the universe. And you might or might not remember, but I reminded you last time, that the gauge symmetry SU2 left keeps you from giving particles mass. Okay? Because in the Lagrangian, the mass squared term, and I don't really remember what it looks like. Oh, no, hold on. No. I got it. I'm just making this shit up. Psi bar, psi. Okay, but the important point is that for this term to exist, it has to be invariant, but this SU2 left gauge symmetry is only acting on the left-handed components. So it's obviously going to mess this term up. Okay? Of one of the terms. So the mass squared's got to be 0 for all the particles because of this symmetry, but it turns out that if you couple all of the matter fields, if you begin with them being massless, but you give them a coupling to the Higgs field, then you can play the same game. You can break the symmetry and give masses to all of the matter particles, or as many of the matter particles as you feel have a mass. Okay? And again, that's a very important, crucial detail in the standard model, but it's way more than I want to go through. Now I want to ask the following question. Did the Higgs field start out up here? If so, how the hell did it get there? Because if our universe is governed by this potential, it just seems like you'd hang out in this circle. You wouldn't sit at that unstable point. Okay? And by the way, hopefully everyone knows what a tachyonic fluctuation is indicating to us in a field theory now. A tachyonic fluctuation is not corresponding to particles which move faster than the speed of light. A tachyonic fluctuation is just saying, you're unstable. You need to get the hell off of your peak and roll down to a stable solution. Okay? And by the way, if you work out a theory, a slightly more sophisticated theory, say string theory, and you discover that there are tachyons in it, you don't sit there and go, oh, those are strings that move faster than the speed of light. You say, oh shit, my solution is unstable. What is it going to decay into? It's my PhD thesis if you'd like to read it. But anyway, but I would like to ask the question, in this story where we start out with this symmetry because we're sitting on this solution instead of this solution, how the hell did we get there? Well, let's consider the history of the universe in a few moments. All right, so going back to our two-dimensional example. Don't need that either. All right. So I want you to imagine, and we're just going to go back to the two-dimensional example. I want you to imagine that the potential has evolved. So the potential is currently this guy right here, where we know that if you were in this solution, you would at some point, because you're fluctuating, you would at some point fluctuate off of that unstable equilibrium, and you would roll down here, and then you would enjoy all of the Higgs mechanism. But what might this look like earlier in the universe? Well, what if here the potential looked like that? And then, throughout the aging of the universe, it sort of develops these features and eventually morphs into this form. Yeah, go ahead.
By aging, do you come out of time? An amount of time?
Yeah, I'm going to go into that in just a minute. But all I'm saying is, let's pretend that the effective potential, or the potential governing your theory, is not fixed. The potential can evolve. Okay? If it was at an earlier point in time, if it looked like this, what is the solution for a constant field configuration? It's 0. Okay? And it remains 0 here, but then once this dips down far enough, it's now unstable. Go ahead.
What kind of thing would cause a change in the potential?
That's what I'm going to explain to you.
Okay.
That's a good question. Okay? So, but what I want to point out is the lowest energy solution in this case is symmetric under SU2 left cross U1y hypercharge. I mean, let's just pretend that this was the potential for that gauge symmetry. This one is still symmetric. The lowest energy solution is still symmetric. But now we see that the lowest energy solution has broken the SU2 left cross U1 down to the U1 of electromagnetism. Okay? So now, ideally, this would happen in the order of increasing time, because we observe this now, and to explain how you got there, earlier in the universe, you would have the potential look something like this. Go ahead.
Is there like a time when, I guess, or the time when you have that center as stable and the circle is stable as well? Or is it a shift straight from one being stable to the other being stable?
Oh, yeah, this is just a cartoon. Don't worry about the cartoon. I mean, the reality of this using this is obviously way more complicated than the picture I'm drawing, so I wouldn't put too much weight to the picture I'm drawing. Yes?
Would that then mean that there's the possibility that this keeps evolving?
Sure.
And then what does
Sure.
that?
But let me finish with what I was saying. I got an important point to make. So, why does the potential change with time? Why would the potential change with time? Ross, you got a guess?
If there was some other fields?
No. I mean, that could influence it, but that's not what we need. So I have to ask you all a question which a few people in the room better know the answer to. Most of you will know the answer. What has happened to the universe over time? It's expanded. Okay? Now, it might be obvious, having stated that it expanded, but what do you think the energy densities in the universe were like 3 seconds after the Big Bang compared to now?
Probably a little faster.
Way higher. Way higher.
A little toasty.
Little toasty, okay? So we can think about this as the axis of increasing time. And we can think about this as the axis of decreasing energy or increasing time if you go back, or increasing energy if you go backwards in time. Okay? Now the reason I want to bring that up is because there's something that we're going to learn at the end of this course. Go ahead.
Energy or energy density?
Energy density, but you can, I mean, you can pick a volume and you can talk about the energy in that volume.
Or are we
But
saying that energy is still conserved, or?
Yes, the energy of the entire universe is conserved, and it's, yes, yes. Okay, but here's the important observation, which hopefully will excite you for learning about this later on. And this is one of the last things that we're going to learn in this class, but it will open the doorway to simple modifications like string theory. If I write down a Lagrangian, you know, it's got mass terms, it might have some mu squared term, it might have some coupling terms, which, you know, this multiplies phi star phi, this multiplies, or phi star phi squared. You know, you have all these constants in there, you know. And I can ask you the following question. Are they constant?
Not necessarily. Not necessarily.
That's a lot. You think they change?
Why not?
What causes them to change? Well, what we're going to learn about towards the end of the course, after we've learned to do Feynman calculus, is that most of these constants in a Lagrangian must change due to renormalization. How many of you have heard that word? Okay. Renormalization is effectively taking the constants in a Lagrangian, taking into account all of the quantum contributions, and realizing that those constants actually depend on the energy. So what that means is that mu and lambda, which are the two parameters that govern this potential, mu and lambda at this end have very different values than mu and lambda at this end. And you can simply imagine that at high energies, mu and lambda were such that this was the shape of the potential. And then through the cooling of the universe due to its expansion, they renormalize to these values, which correspond to that shape of the potential. Avery, you got a question?
Does that say that energy in the universe has changed?
I'm not talking about the energy in the whole universe.
Yeah.
I'm talking about the energy on a given scale, like 1 meter.
Okay.
How much energy is in a sphere of radius
Okay.
1 meter, and it's less energy in a larger universe.
Yeah.
Okay? Okay, so we're going to learn about this, but does this reasoning make sense as to why there would have been a historical evolution of the potential? Okay? It's not necessarily time itself, but rather the fact that if the universe were sitting still and it wasn't expanding, if it was static, which is what Einstein hoped he'd achieve by his cosmological constant, but if the universe was static, this shit wouldn't happen. But the universe is expanding, energy is getting smaller in a region, and that is causing renormalization, which is shifting the constants which define the potential curve, and it could shift it from this to this. But of course that means that you could start out naturally in that solution, which is the lowest energy solution, but eventually find these solutions which break the symmetry. Okay? Yes?
So I reiterate my earlier question, does that keep evolving then? And if so, what into?
We don't know. We don't know.
We don't know how this evolves?
Well, actually, I am not intimately familiar with the potential associated with this breaking of the symmetry. But there are speculations that, actually, I don't know if you can break the U1 spontaneously. There's certain aspects of a U1, it's such a simple group that I believe you can't even apply the Higgs mechanism to break a U1 by itself. You need something that's not abelian. But my guess is, the expectation is that once you've evolved into this shape of the potential, you probably won't change the overall shape. You might change the steepness of things, but you're going to maintain this valley of lowest energy states. Yeah.
In your experience of higher dimensional theories, does the symmetry still break?
I'll get to that in a minute. I will. But this might all seem really strange. You know, high energies, things are symmetric. Low energies, things are not symmetric. Sounds like bullshit, right? Let me show you an example which will hopefully be very familiar to you. So I want you to imagine a gas, or no, actually a solid, of magnetic monopoles. Okay?
All right, sounds like thermal physics. I'm out.
No. It's actually pretty simple. At high temperatures, which is high energies, okay? I want you to just answer this question. At high temperatures, really high temperatures, do you believe that the magnetic monopoles are oriented with each other? No, they've got so much energy that they're wiggling like a mofo, and this guy's going to be like, screw you, I'm going to point this way, I'm going to point this way, oh yeah, I'm going to point that way, I'm going to point this way, I'm going to point this way. They can point in any damn direction they want.
What do you mean?
Okay?
What? I don't,
What?
how do they have a direction?
They're magnetic sorry, not monopoles. Yeah, thank you, magnetic dipoles. Yeah. No, it's because I was talking to some people on Monday, and I was getting into the foray of magnetic monopoles as a dual description of electromagnetism, and it just stuck in my brain. But anyway, that is not like, shut up, Sarah. Anyway, okay, ready? What happens when we start to lower the temperature?
They align.
They align because you remove the kinetic energy. They don't wiggle as much, and their mutual interaction is at some point going to pick up. And if you get the temperature low enough, the mutual interaction will dominate and they will align. What direction will they align in? Whatever direction. So maybe it's that direction. But there you go. Now, I really need you guys to think broadly, because I know in this situation at high energies we had more symmetry and at low energies we had less symmetry, whereas in this case at high energies we have less symmetry and more. Wait a minute. Which of these has more symmetry?
The first one.
The first one. Because if everything is completely randomly oriented, what rotational invariance do you have?
Whatever.
You have SO3. What about here?
SO2?
You have SO2.
Oh, hell no.
Okay? This story can be told exactly through the Higgs mechanism. You can write down a Lagrangian, you can talk about finding a solution to an effective potential, okay? And that solution breaks the symmetry. Yes?
Does that mean we have some sort of bifurcation between these two things, or is it more continuous than that?
Bifurcation?
Bifurcation.
So if you dial, I mean, look, if you dial it down, there's going to be my guess is that it's a continuum, and in principle, unless you take the temperature to infinity, you're always going to have a mild alignment that will grow stronger and stronger as you reduce the temperature. However, the directionality of that alignment, I don't think it can be established Yeah, I'm not, yeah, if you take this and heat it up versus cooling this down, if you take this and heat it up, these things will start vibrating or spinning around more independently, and the question is, do they ever actually achieve this full SO3 invariance? Are they completely random? And I would have to look more into the details of the underlying Lagrangian. Bye, Avery. It's okay. I'd have to look more into the details of the underlying Lagrangian. I mean, if you're just, yeah, I'll have to look into it. Okay. However, I do want to point out one more striking similarity between this and the Higgs story, which I told you. Which was in the Higgs story, you might remember that we had this nice Mexican hat potential, and these lower energy solutions, even though they break the symmetry, okay, they do it in a spontaneous manner. There's nothing that says you have to go to this solution. You might roll to this solution, or you might roll to this solution. So the word spontaneous is inserted in there, spontaneously broken symmetry, okay? There's just a random element to the story. Is there a random element to this story? Yes. It's what axis these things finally pick to align on. That is exactly analogous to the yes, to that case. All right. So we've got spontaneous symmetry breaking as the underpinning incident that incorporates all of this Higgs magic. And I'm going to finish, actually I'm amazed that I'm getting through 6 slides. I'm going to finish with a comment that is trying to intuit this, and then a comment which goes a little bit beyond it. But is one of my favorite illustrations of why string theory rules the great Earth. So, first of all, I think I told you very, very early this semester that field theory was important. Way more important and useful than just focusing on particles. Does anybody remember one of the reasons why I said field theory was such an important tool to make use of? Sarah? What are the particles, what characteristic or attribute of the field does a particle correspond to?
Just a fluctuation?
It's just a fluctuation, okay? Well, if we just dealt with fluctuations or particles, we could probably scrap the whole field description. But sometimes we have an element to our story where just the fluctuation doesn't tell it all. For example, in the Higgs mechanism, where the field everywhere starts out at the top and the field everywhere rolls to the value at the bottom. That is not a story of a fluctuation. That's the story of the field everywhere in the universe. If you relegate your story just to fluctuations, you're doing what's called perturbative physics. You're just dealing with perturbations, small particle-like behaviors. But things like the Higgs mechanism, where the background field everywhere in space-time shifts its value from this symmetric point to the asymmetric point, that's called a non-perturbative effect. Okay? And what I want to do is I want to just draw a picture of what one way to intuit non-perturbative versus perturbative effects. So suppose that your quantum field was a lake. Sure. So if your quantum field was a lake, then particles are ripples on the surface of the lake. Okay? So your field is the water in the lake. It's everywhere. And a small fluctuation on the surface corresponds to a particle. All right? Now this field is actually coupled to another field. What field do you think the water in a lake is coupled to in terms of a field in this analogy?
Like air?
It's actually not so much coupled. It is kind of coupled to air, but what is it more importantly coupled to? The ground underneath it.
Okay.
Okay? So the picture that I'm thinking of is so we have the ground and we have water. Okay, there's our illustration of a lake. And we have fluctuations in the water, which are particles. And if this is the shape of our ground and this is the shape of our lake, this is the field configuration, then you know how these ripples are going to behave. So for example, if you throw a rock in and start a ripple, and it's in one spot, it's just going to sit there. I mean, it'll migrate out, but it'll just sit in that one spot, right? Okay? Now what I'm going to do is I'm going to create a non-perturbative effect in the field that the lake is coupled to.
But all the water's gonna spill out.
So we have to have in mind that this is being sourced by something, maybe a lake or a river that's flowing into it. But anyway, my point is that this shift in the configuration of the ground, which the water is coupled to, changes the overall field configuration of the water. There'll be a waterfall here. But what's important is that modifies the behavior of the fluctuations. If you throw a rock in here and you get a little ripple, that ripple is going to run over the waterfall. Very different than the behavior of a ripple here. Make sense? So when we do particle physics, we're often focused on the ripples, the little particles, because that's what we're banging into each other and watching come out in experiments. But a very, very important and in many cases undetermined aspect of the standard model is, what does the underlying field configuration look like? Okay. And it turns out that for the strong interactions, it's still undetermined exactly what the underlying field configuration of, say, the gluons look like. It could be something really wacky. All right? Now, I just want to give you, perfect, five minutes. I just want to give you a picture of what the Higgs mechanism looks like in string theory. And you might ask, or you might say to yourself, he's going to do string theory. Shit, that's going to be hard. I will argue that what I'm about to show you makes the Higgs mechanism so much easier than doing it in particle physics.
You're going to draw it in 11 dimensions?
No, I'm not.
Well, yes.
That's a good guess, though. Okay? So first of all, I'm just going to talk about breaking a gauge symmetry down from one group to a smaller group. Okay? And we know that in breaking the gauge symmetry down, we have to give things mass. But we have to ask, how do gauge symmetries arise in string theory? Well, gauge symmetries arise in string theory because of the existence of these things called D-branes.
Oh, yeah.
D-branes are hypersurfaces, so string theory exists in 10 dimensions, and so you can think of a 5-dimensional surface in 10 dimensions, or an 8-dimensional surface, or a 9-dimensional surface, or a 1-dimensional. So you can think of these different surfaces, and what's important about those surfaces is that if I have a surface, so it goes into the board, then you have closed strings which can propagate throughout all of space-time, but an open string, a string which has two ends, must begin and end on the D brane. Okay? All right? Now, what's interesting is if I take two D branes, then they each have a variety of open string which ends on that D brane. But if they're close enough, I can have open strings which stretch between the two D branes. Yes?
These D branes are like non-physical things, right? Like it's
They are
just a
non-perturbative.
Okay.
The strings are the perturbations, the D branes are non-perturbative backgrounds. They're not fields, they're just these big walls. And don't think of the wall as made of matter.
Right.
Okay, but here's the thing. These open strings correspond to gauge fields. Each open string corresponds to an a mu gauge field. So if I have one D brane and it has one gauge field, what do you think the gauge symmetry is?
U1.
U1, because U1 has one generator. If I have two D branes that are close enough to extend open strings between them, this one is, they're oriented in different directions. What gauge symmetry do you think this represents?
SU2?
It represents U2, actually, not SU2. Okay? And you can extract the overall motion of the D brane for getting it down to SU2. But anyway, we'll just count the number of strings right now. So this corresponds to a U2 symmetry. We could, of course, add another D brane. It will have its own. What symmetry do you think that describes? U3, okay, 9 gauge fields. SU3, the standard model of quantum chromodynamics, has 8 gauge fields because of the S. But here you can literally count. There are 9 open strings. All right? So, I mean, screw that. If I just draw 3D branes and say how many gauge fields are there, you can count. There's 9. It's wonderful that way. And then you can later associate that with the U3. All right, now these D branes would actually be coincident. They would actually be right on top of each other. They wouldn't be separated at all, but drawing 3 coincident D branes is kind of redundant, okay? But now, nice.
Now the Jesus music.
You ready?
Yeah.
What happens if we take these 3 D branes and we separate one of them? Well, what happens? You have a particle on each D brane. You have the particles between these 2 D branes. And you have the particles between these 2 D branes and these 2 D branes. And now I've got to give you one piece of non-intuitive information. Strings are extended. They don't have a mass, they have a tension. Their mass is their tension times their length. This is effectively 0 length. So these are massless string states. However, what do you think about these 4 string states? They become massive. What do you think is the symmetry of this?
SU2 cross U1.
U2 cross U1. It's okay. Because of your 9 generators or gauge fields, 4 of them became massive. You're left with the U2 for these 2 D branes and the U1 for this one. These 4 gauge fields gained mass. That sounds a lot like the Higgs mechanism. But you want to hear the most awesome part of this story? Yeah, you do. What do you think is the Higgs field? The Higgs field was that crazy thing that was coupled to shit, and when it achieved a non-zero expectation value, things got mass. What in this story do you think corresponds to the Higgs field?
Separation.
It's the distance between the branes. Yes.
So how do you move one away?
Grab it, pull it. Don't worry about it. Don't worry about it.
Erase it in your
All right, that's enough for today. Let's all go home. Hey, you guys remember your exam on Thursday.
Yeah.
It hinges on you studying homework solutions. Except for the 2 homework problems that I assigned for Thursday, but those are going to be on the exam, and that's all about the Higgs. Those are the 2 problems, right?
Wait, homework solutions or homework quiz solutions? Or
Homework quiz solutions. No, homework solutions. Well, homework
Okay.
and homework quiz solutions.
Okay.